Usually when we talk about a medical diagnosis, there's this expectation of absolute precision.
Right, like it's an exact science.
Exactly. It feels like pure engineering. Like you break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is, that's the problem.
Yeah, it's very visible, very straightforward.
But then you step into the world of global logistics and supply chains, and you suddenly realize the true engineering marvel isn't always the visible product itself.
No, it's really not.
It's the invisible armor protecting it. I mean, think about it. You order a delicate glass vase and, say, a 50-pound cast iron kettlebell.
Right.
They both cross oceans, ride on trucks, get tossed onto these massive automated conveyor belts, and they arrive at your doorstep in absolutely perfect condition.
It is honestly a minor miracle of modern commerce that we just take entirely for granted.
We really do.
We tend to just look at a cardboard box, open it up, and throw it in the recycling bin, completely ignoring the intense calculation that went into its design. The reality of how that glass vase actually survives its journey is, well, it's anything but simple.
Exactly. And that is our mission for you on today's deep dive. We are exploring the hidden, high-stakes puzzle of industrial packaging.
It's a fascinating topic.
It really is. To do this, we are diving deep into the AP Certified in Logistics, Transportation, and Distribution Manual.
Which is essentially the gold standard text for supply chain professionals.
Right. And using it as our guide, we're going to look at how packaging is actually this massive collision of physics, economics, and environmental science.
So, okay, let's unpack this.
Yeah.
And yeah, pun entirely intended.
It is a great pun, I have to say, and highly accurate for the journey we're about to take. What we're really going to examine today is the intersection of geometric efficiency and risk management.
So, to even begin designing a packaging strategy, you have to deeply understand the physical state of the product you are moving, right?
Absolutely. The APCS manual draws this very clear line between consumer packaging, which we all know is about shelf appeal and marketing.
Bright colors, nice fonts.
Right, exactly. It separates that from industrial packaging, and the goals of industrial packaging are just ruthless.
Very much so.
It's about pure protection, minimizing cubic volume and weight, and maximizing handling efficiency. And those goals change drastically depending on whether you are moving, say, a solid or a liquid.
Yeah, the physical state dictates the entire logistical architecture, really. Take liquids, for example.
Okay.
The manual points out that you have to account for viscosity.
Which is the fluid's resistance to flow, right?
Exactly. But the trick is, viscosity isn't static. It changes depending on the ambient temperature during transport.
Oh, right. So how does that temperature fluctuation actually impact the physical packaging design?
Well, it forces logistics engineers to design containers that can handle dynamic internal forces. Like if a liquid becomes highly viscous, essentially turning to sludge in freezing temperatures, the packaging might require specialized wide-mouth dispensing mechanisms.
Just to get it out of the container.
Right, or even built-in heating elements.
Wow.
And conversely, if temperature spikes cause the liquid to expand or thin out, the packaging needs really precise headspace calculations.
So it doesn't just explode.
Yeah, exactly. So the drum or the intermediate bulk container doesn't rupture from all that internal pressure.
That makes a lot of sense. The product literally fights the packaging.
It does.
And the source goes into some fascinating detail on bulk solids, too, like coal or iron ore. Obviously, you don't package those in individual cardboard boxes.
No, definitely not.
But you still have to understand their physical properties to move them, specifically this concept called the angle of repose.
Ah, yes, the angle of repose.
The manual says iron ore has an angle of repose of 35 degrees, while anthracite coal is only 27 degrees. What does that actually mean for the logistics planner trying to move this stuff?
So the angle of repose is basically a measurement of how high you can stack a loose material before gravity causes it to slide down into a flatter pile.
Okay, I can picture that.
Because iron ore has a steeper angle of 35 degrees, it forms a tighter, taller peak.
Right.
Anthracite coal at 27 degrees is much looser and spreads out significantly wider. Operationally, this dictates the geometric design of the storage silos.
Oh, wow.
Yeah, and the draft and width of river barges, and even the structural reinforcement of the retaining walls in a freight yard. A logistics planner literally has to allocate a much wider physical footprint to contain the coal compared to the iron ore, simply because of how the particles interact with gravity.
And allocating that footprint brings us directly into the ultimate constraint of all freight transportation, which is density. The manual highlights this constant, brutal battle between weighing out and cubing out.
This is the fundamental math of the freight industry.
Yeah.
Every single vehicle, whether it's a long-haul truck, a rail car, or a massive cargo ship, is bound by two strict limits, a maximum weight limit and a maximum cubic volume limit.
Right. It's basically like packing a suitcase with bowling balls versus packing it with pillows.
That is a perfect analogy.
So a planner moving heavy machinery parts, the bowling balls, is going to hit the legal weight limit of the truck chassis long before they fill the physical space inside the trailer.
Yes, they have weighed out.
Meanwhile, someone shipping fiberglass insulation, the pillows, is going to fill every single inch of the trailer from floor to ceiling, but the total load might only weigh a fraction of the truck's capacity. They have cubed out.
Exactly. And that mathematical reality dictates your shipping costs and your packaging strategy.
How so?
Well, if you consistently weigh out, your packaging needs to focus entirely on structural integrity to support massive localized weight. But if you consistently cube out, every millimeter of your packaging thickness is scrutinized because you are fighting for cubic volume.
Add in the requirements for contamination prevention, and the puzzle gets even harder. The manual notes that if you're moving pharmaceuticals or food, you have to design packaging that prevents biological contamination, maintains a strict cold chain.
Which is incredibly difficult.
Yeah, and sometimes even withstands aggressive sterilization processes like irradiation without the plastics degrading.
The material science required to create a sterile, temperature-controlled, impact-resistant barrier is just incredibly advanced.
But let me push back on this underlying philosophy for a second.
Okay, go for it.
If the primary goal of industrial packaging is to protect the product at all costs from temperature, impact, and contamination, why not just wrap absolutely everything in a foot of heavy-duty, climate-controlled bubble wrap? Where is the line between protecting the goods and just wasting space?
If we connect this to the bigger picture, the line is drawn by the brutal economics of logistics. In supply chain management, you pay for space. If you wrap a product in a foot of unnecessary bubble wrap, you are vastly increasing the cubic volume of that item. If you do that across 10,000 units, you suddenly need 5 trucks instead of 1.
Oh, wow. Yeah.
You end up paying astronomical freight rates just to ship empty air.
You're paying to move the protection, not the product.
Precisely. The manual refers to the solution as design for logistics. IKEA is the classic example outlined in the text.
Oh, of course. Flat packing.
Exactly. They don't ship fully assembled armchairs wrapped in layers of padding. They ship ultra-compact, dense kits. By redesigning the product itself to lay flat, they maximize the utilization of their transportation assets. They eliminate the air before the packaging is even applied.
So assuming you can't re-engineer your product into a flat pack kit, how do you actually balance that necessary physical protection with intense space efficiency?
That is the big question.
And the source material explains this through what they call the building blocks concept.
It's an aggregate system, really. Because you can't rely on a single, massive layer of bubble wrap to do everything. You use successive layers of packaging that work together mathematically.
Okay.
The manual divides this into 3 distinct layers.
Layer 1 is the primary layer. That's the consumer packaging, like the glass bottle holding olive oil or the sterile blister pack for a pill.
Right, the stuff you actually see on the shelf.
Exactly. It touches the product directly and handles the immediate moisture or dust protection. But layer 2, the secondary packaging, is where the math really starts. This is the master carton.
Yes, the master carton groups multiple primary units together to enable efficient handling. But the design of that carton is fiercely debated.
Because of carton efficiency. The manual details how designers have to calculate the cubic space of the actual products and divide it by the total cubic space of the master carton.
And that's where things get tricky.
Right, because if you put 6 round bottles into a rectangular box, you inherently have empty space in the corners between the curves.
Yep.
Your carton efficiency drops. You are shipping air inside that box, which we just established is a massive waste of money.
Designers try to optimize those internal voids, but they are simultaneously constrained by the external dimensions of the box.
Right.
This introduces the principle of modular packaging. The goal is to design various sizes of master cartons as exact mathematical fractions of a standard pallet footprint.
So the carton's length, width, and height are engineered so that when you stack them, they form perfectly even, flush layers.
Exactly. If a carton is properly modular, there is 0 overhang, which prevents the boxes from crushing under their own weight.
Oh, that makes sense.
And there's 0 underhang, meaning you utilize 100% of the pallet's expensive cubic space.
Okay, so you have your primary bottle, your mathematically perfect secondary master carton, and then layer 3, the tertiary layer, which is the unit load itself, and something called dunnage. Now, dunnage was a new term for me.
Dunnage refers to the materials used to fill voids, block, and brace the load to prevent shifting during transit. It's the heavy-duty inflatable bags, the corrugated partitions, the steel strapping. It's essentially the shock absorber for the entire unit.
Here's where it gets really interesting, though.
Yeah.
If companies are so obsessed with modular packaging, meaning they only want to use a limited number of standard, mathematically perfect box sizes so everything stacks cleanly on a pallet, doesn't that create a huge problem for direct-to-consumer shipping?
Oh, it absolutely does.
Like if you order an awkwardly shaped product, doesn't it just end up floating in an oversized standard box, completely filled with those inflatable dunnage bags?
You've identified a massive unresolved tension in modern supply chains.
Yeah.
The source confirms this is exactly what happened.
I knew it. I feel like I get packages like that all the time.
We all do. To keep their warehouse automation and pallet building efficient, facilities strictly limit their box sizes. But that standard limitation means many boxes are grossly oversized for the specific item inside. It is a major supply chain inefficiency. However, regarding the protection aspect, it's important to remember that impact, vibration, compression, and puncture resistance is a cumulative team effort.
Ah, okay.
The primary bottle, the secondary carton's corrugated fluting, and the tertiary dunnage all work together to distribute kinetic forces away from the product.
It's an incredible system, but this hyper-focus on modular cartons creates a new logistical hurdle. Once these boxes are taped up and perfectly flush, they are essentially identical, anonymous brown cubes.
Yes, they are.
If you've got a distribution center with millions of them moving at high speed, how does the system know what's inside without opening them?
They need an identity, and that requires strategic labeling, which is usually applied at the very end of the production line. And it's far more complex than just sticking a barcode on a box.
The strategy detailed in the source is fascinating. Like if you are shipping high-value items, laptops, pharmaceuticals, designer goods, you absolutely do not print a description of the contents on the outside of the box.
No, the risk of pilferage during transit is just way too high.
Right.
Supply chains use coded labels that integrate with their internal warehouse management systems, completely obscuring the contents from anyone physically handling the box.
And the international regulations surrounding these labels are a total minefield. The manual points out that if you don't list the metric system first on your labels, certain countries will hit you with immediate fines or just flat out reject the freight.
Yes.
Canada has incredibly strict bilingual labeling rules, and domestically in the U.S., individual states have granular laws about the exact font type, size, and placement you have to use for liquor labeling.
The label is a legal document as much as a routing tool, really. But once that identity is established, the individual master cartons must be consolidated. This is the process of unitization.
Taking all those individual boxes and combining them into one larger unit, usually a pallet, and the efficiency gain stated in the APS manual is staggering. It says a unit load can be unloaded from a truck 5 times faster than a load of loose master carton.
That speed translates directly to cost savings. Carriers, the companies actually operating the trucks and ships, structure their pricing tariffs to force manufacturers to unitize and densify their freight.
How so? Like, how do they force them?
They publish different rates based on the state of the packaging. For instance, they charge entirely different rates for SU, which means setup packaging, where a product is fully assembled and bulky,
Okay.
versus KD, or knockdown packaging, where the product is disassembled and dense.
Oh, I see.
Planners have to calculate the relative density of the load in advance, and carriers offer lower freight classes and cheaper rates for KD packaging to basically incentivize shippers to maximize the carrier's vehicle capacity.
Which logically brings us to the environmental impact of all these materials. Everyone wants sustainable packaging, right?
Of course.
The obvious goal outlined in the source is to minimize the weight and volume of the packaging, use recycled materials, and comply with international law. The European Union is driving this hard with Directive 9462/EC and the pending PPWD, which basically mandates that all packaging must be recyclable at scale by 2030.
But the manual emphasizes a crucial point that often gets lost in the public debate about zero-waste packaging.
What's that?
Wasting the product itself is almost always a worse environmental footprint than the packaging used to protect it.
That feels really counterintuitive to the average consumer who's just looking at a pile of plastic wrap.
It does, but you have to consider the total life cycle. If a shipment of perishable food spoils or a pallet of delicate electronics is crushed because a company skimped on protective plastic shrink wrap,
Right.
all the water, fertilizer, rare earth mining, energy, and transportation fuel that went into creating and moving that product is entirely wasted.
Oh, wow. I hadn't thought about it like that.
Yeah, that net environmental loss far exceeds the impact of using robust, albeit non-recyclable, protective packaging.
I understand the spoilage argument, but let me challenge the long-term solution here.
Sure.
A major push in sustainability is transitioning to reusable packaging. The source talks about rigid, stackable plastic bins, heavy-duty kegs, returnable dunnage. On paper, eliminating single-use cardboard sounds like a massive win. But doesn't someone have to pay the fuel and transportation costs to ship all those heavy, empty plastic bins all the way back to the manufacturing plant to be refilled?
What's fascinating here is that you've zeroed in on the exact calculation supply chain managers wrestle with every single day.
Really?
Yes, the reverse logistics for empty containers carries a massive environmental and financial cost. You have to calculate the total environmental footprint over the entire life cycle, not just at the unboxing stage.
Right.
In many scenarios, a lightweight, single-use, fully recyclable cardboard box actually generates a lower total carbon footprint than a heavy, durable plastic bin that requires diesel fuel to be transported back and forth thousands of miles while totally empty.
That is wild.
Sustainability in packaging is a highly, highly delicate balancing act.
It's a massive, hidden trade-off. And speaking of hidden foundations, the ultimate enabler of this entire unitization process, the unsung hero of global trade, is the pallet itself.
The pallet is the fundamental matrix that the modern physical Internet of Goods is built upon.
The manual breaks down the variations. Most are made of wood, though some are plastic or composite. You have two-way entry pallets, where a forklift can only engage it from the front or back,
Right.
and four-way entry pallets, which allow forklift access from all four sides, offering much more flexibility in a tight warehouse. But the detail I found most incredible was the IPPC ISPM 15 mark.
Yes. The International Wheat Stamp.
Yes. If you walk into any warehouse and look closely at the side of a wooden pallet, you will often see this little symbol branded into the wood that looks like a stalk of wheat. That stamp proves that the raw wood was either heavily heat-treated or chemically fumigated.
Yep.
I always just assumed pallets were, cheap scrap wood. Why go through the expense of fumigating them?
It is a matter of strict global biosecurity.
Biosecurity?
Yeah, because these wooden platforms cross international borders constantly, they can harbor invasive pests, insects, and fungi deep within the grain.
Oh, yeah.
The ISPM 15 regulation prevents a beetle from a forest in Asia from hitching a ride on a pallet and decimating a localized ecosystem in North America.
So it's international ecological defense hiding right there on a piece of warehouse equipment.
Exactly.
Now, while wood pallets are the standard, they are heavy, and they take up roughly 6 inches of vertical space per pallet. In a truck holding 30 pallets, that's a lot of lost cubic volume.
It adds up fast.
So the industry developed an alternative, slip sheets.
Slip sheets are a brilliant exercise in minimalism.
They really are. They're basically just thin sheets of highly durable plastic or fiberboard with a reinforced lip folded up on one edge. They take up virtually zero vertical space, and they weigh almost nothing, completely solving the density and weight limits we talked about earlier.
Right.
But obviously, a standard forklift with 2 metal tines can't pick up a flat sheet of plastic. How do they actually move these things?
That is the operational catch. You cannot use standard equipment. Both the shipping facility and the receiving facility have to invest in specialized push-pull forklift attachments.
Okay, how does that work?
Instead of forks sliding under a pallet, this attachment features a heavy hydraulic clamp. It reaches out, grabs that reinforced lip on the slip sheet, and literally drags the entire 1,000-pound load onto wide steel plates resting on the forklift.
Wow.
And then when it drops the load off, the mechanism pushes the freight forward while pulling the steel plates back.
It's a huge equipment investment, and the manual notes that unlike sturdy wooden pallets, slip sheets generally aren't reusable.
No, they get damaged by the clamping mechanism.
So you trade space efficiency for equipment costs and single-use materials.
Every logistics decision is a compromise.
Which brings us to the final and maybe most surprising compromise in the manual: the physics of stacking. Assuming you have your pallet, you have to stack your modular master cartons on top of it. The manual explains pallet load efficiency, which is your carton efficiency multiplied by how perfectly those cartons cover the pallet footprint. But then it dissects the actual geometric pattern used to stack the boxes.
Mm.
Block stacking versus brick stacking.
The geometry here dictates the survivability of the load.
Okay.
Block stacking is exactly what it sounds like. You stack the boxes directly on top of each other, creating perfectly straight vertical columns.
Then brick stacking.
Brick stacking involves interlocking the boxes like a traditional brick wall, rotating each layer 90 degrees so the seams overlap.
Right. And reading this section, I had a massive aha moment regarding the structural engineering of a cardboard box.
Oh, yeah.
Think about a standard corrugated box. The strongest structural elements are the four rigid vertical corners.
Yes.
The absolute weakest part of the box is the dead center of the side panel, where there's no vertical support.
That is physically correct. The corners bear the compression load.
So if you use a brick stacking pattern to interlock the boxes, you are intentionally taking the heavy, solid corners of the top box and resting them directly in the middle, the weakest possible point of the bottom box.
Yep.
Why on earth would warehouses deliberately sacrifice the structural integrity of the boxes and invite crush damage just to overlap the layers?
It is the ultimate stacking paradox, and supply chain engineers debate it constantly. By brick stacking, you drastically reduce the vertical crush resistance of the bottom layers. You are introducing shear force to the weakest part of the corrugated board.
So why do it? Like, what's the benefit?
Because of the dynamic forces of transportation. Load stability during transit is often deemed more critical than pure crush resistance.
Oh, I see.
A straight vertical block stack has very little lateral cohesion. When a forklift takes a sharp corner or a truck hits a pothole at highway speeds, a block stack will easily shear and topple over, ruining the entire pallet.
That would be a disaster.
Right. Brick stacking locks the layers together, preventing lateral tipping.
So you accept a certain amount of crush damage to prevent the entire load from collapsing.
Exactly. And to compensate for that weakened crush resistance, warehouses are forced to reinforce the outside of the brick-stacked pallet using heavy-duty plastic stretch wrap, specialized adhesives between the layers, and rigid corner guards to essentially build an external skeleton for the unit load.
Wow. So what does this all mean? We started this deep dive talking about a glass vase and a kettlebell. What we've discovered through this Epices manual is that industrial packaging is this vast, highly engineered hidden world where material science, intense geometric fractions, and international biosecurity laws collide.
It's all connected.
Every single anonymous brown box sitting flush on a wooden pallet in a warehouse is the result of a fierce mathematical negotiation between weight, volume protection, and cost.
It truly is a marvel of human optimization and standardization.
Yeah.
But I want to leave you with a final thought. Looking beyond the current system, we've spent this entire time analyzing how humans design modular, rectangular boxes to fit perfectly on standard square pallets. But what happens to the global supply chain when artificial intelligence takes over packaging design?
Oh, wow. Where does that lead?
AI isn't constrained by our traditional human bias toward right angles and simple geometry.
Right.
We might soon see AI generating hyper-optimized, strange, non-standard geometric shapes like incredibly complex 3D puzzle pieces that interlock perfectly to fill the exact dimensions of a shipping container.
That's crazy to think
They
about.
could completely eliminate every cubic inch of empty air, abandoning the traditional square cardboard box we've relied on for over a century. The raw mathematics of efficiency will simply outgrow the box.
That is a wild image. An entire massive cargo ship loaded with interlocking 3D puzzle pieces designed by an algorithm to cheat the laws of volume. I love that. Well, thank you for joining us on this deep dive. The next time you find yourself wandering down the concrete aisle of your local big box warehouse store, I hope you look up at those towering pallets and uniform brown boxes with a newfound sense of awe. They aren't just cardboard, they are the invisible armor of global trade. We'll catch you next time.